Imagine you point a telescope up at the sky and you pick up a signal so perfect, so regular, that it just feels impossible for it to be natural. Well, this isn't some sci-fi movie plot. It's the true story of a discovery that started with a funny little nickname and ended up completely changing how we see the universe. Let's get into it. Okay, so here's the mystery. You've got this signal pulsing from 2,300 light years away in the constellation Vulpecula. And it's keeping time better than a Swiss watch, a perfect beat once every 1.34 seconds. It was so clock-like, so artificial seeming that the scientists who found it couldn't help but wonder, wait a minute, are we actually alone?
So let's rewind to 1967 at Cambridge University. A graduate student named Jocelyn Bell is looking through just miles and miles of paper from a chart recorder, and she sees this little bit of what she called scruff, a weird signal that just wouldn't go away and pulsed with this insane regularity. The team, kind of half joking but also half serious, nicknamed the source LGM1, and that stood for Little Green Men.
What's so cool here is just how fast this all happened. I mean, think about it. In August of '67, it's just this weird squiggle on a piece of paper. By November, they've confirmed its crazy precision, a pulse every 1.34 seconds, on the dot. That's when that LGM1 nickname really started to stick. And for a few months there, things were pretty tense as they wrestled with what this could mean. But by February of '68, the truth came out. It wasn't aliens, it was the very first evidence of a totally new type of star.
So, if it wasn't little green men, then what in the world was sending this cosmic drumbeat? Well, the answer turned out to be just as bizarre and amazing. A brand new kind of object that astronomers had only theorized about, but had never actually seen. A cosmic lighthouse spinning out there in the dark.
And they called it a pulsar. So what is a pulsar? It's what's left over after a giant star goes supernova and dies. You get this incredibly dense core, a neutron star, an object so dense that a single teaspoon of it would weigh billions of tons. And it's spinning unbelievably fast, all while blasting out these powerful beams of radiation from its magnetic poles. And this is the perfect way to picture it. You know how a figure skater pulls their arms in to spin faster? Same idea. When a massive star collapses down into this tiny neutron star, it spins up like crazy, sometimes hundreds of times a second. The spinning dynamo shoots out beams of radio waves. And just like a lighthouse on the coast, if that beam happens to sweep past Earth with every single rotation, we see a pulse. Blink, blink, blink. And just like that, the mystery was solved. Or so we thought. Because you see, the story of PSR B1919+21, our original little green man signal, is nowhere near over. Decades later, with these unbelievably powerful new radio telescopes, we're looking at the exact same object, and we're discovering that it's even weirder than we could have imagined. The difference is just mind-blowing. Back in 1967, you had paper charts showing a simple repeating blip. The question was pretty basic. What is this thing? But today, telescopes like NenuFAR and the FAST telescope give us such high resolution that we can see the detailed structure inside every single pulse. So the question has totally changed. It's not what is it anymore, it's how does it work? And that new level of detail? Well, it's revealed a whole new mystery. This time, it's not about the timing of the pulses. It's about the very nature of the light itself. Something really, really strange is happening to those radio waves on their long journey from the pulsar to us. Okay, this right here is the heart of the new discovery. In a huge number of the pulsar's flashes, the polarization position angle, which is basically just the direction the light wave is vibrating, is twisting. And I don't mean by a little bit. It's rotating a full 180 or even 360 degrees inside one tiny pulse. Now, to get why that's so nuts, we need a super quick refresher. It's actually really simple. Just imagine you're shaking a long rope. You can shake it up and down, right? Or you can shake it side to side. Light waves do the exact same thing. And polarization is just a way of measuring that preferred direction of the vibration. Normally, for a star that's super far away, you'd expect that direction to be pretty stable. But this is what scientists are actually seeing from PSR B1919+21. In some of these pulses, that direction of vibration does a complete 540-degree corkscrew. That is 1.5 full rotations, all happening in the tiny fraction of a second that the pulse lasts.
This isn't some gentle little curve. It's a really violent, super fast twist that just screams for an explanation.
So, what could possibly twist light that dramatically? How do we even begin to solve this puzzle? Well, it turns out this bizarre effect is actually our ticket to get a look deep inside the pulsar's engine room, its magnetosphere, that super intense, chaotic magnetic field that surrounds the star. And this is the question that astronomers studying this object are asking right now. What can this brand new, strange signal teach us about the physics going on in one of the most extreme places in the entire universe?
And the answer is, this crazy effect isn't just some weird quirk. It's an incredibly powerful diagnostic tool. By analyzing how the light gets twisted, scientists can figure out what it must have passed through on its way here. It's like we're using the light itself as a tiny probe to measure the conditions right above the neutron star's surface.
The best explanation we have right now is something called the phase lag model. The idea is that the pulsar actually sends out two radio waves at the same time, vibrating at right angles to each other. As they fly through that crazy intense magnetic field, one wave gets held back just a tiny bit. That delay is the phase lag. And when that lag changes really fast as the beam sweeps past us, we see it as this massive twist in the light's polarization.
And get this. Here's the scientific payoff. This model doesn't just explain the twist. It lets us calculate where the radio waves are actually coming from. The math points to the emission being born just about 100 kilometers above the surface of the neutron star. Keep in mind, the star itself is only about 20 kilometers wide. We are pinpointing the birthplace of this light with incredible accuracy.
And that's really the big takeaway here. A journey that started with a little bit of scruff on a paper chart, a joke about aliens, has led us all the way to this. We can now use the light from PSR B1919+21 to make actual, concrete measurements about what's happening in a place we could never, ever hope to visit.
So that leaves us with a pretty cool thought. This was the very first pulsar ever found. We've been studying it for over 50 years, and it is still surprising us, still giving up secrets that only our newest and best technology can unlock. And since then, we found nearly 3,000 other pulsars. So you have to wonder, what other incredible discoveries are just waiting out there for us, hidden in those cosmic lighthouse beams?